Yeah. Oh, okay. It's perfect. Well, no, it's not. But half the part is electric, so it's going to be much.
I'm working.
Okay. Okay, so now we're going to talk about adaptive sampling. So now that we've introduced the Markov models, so I'm going to talk, I don't know, so how many people are familiar with adaptive sampling here? Okay, so I'm going to present in general here first, and then go a bit into more details. So practically when we used in the past to do all of our simulations, we did them in a high-throughput manner where simulations were a bit stupid. So we started, for example, all of our simulations from the unfolded conformation or from the bulk conformation if we were doing protein ligand binding. Then we simulated a bit and we might have explored all of this space here, for example. Now, if we didn't find our bound or our folded, we started new simulations, but we started them again from the same initial conformations, which is a waste of time because if you are unlucky, you might just not learn anything new. On the other hand, you can do it obviously in much more intelligent ways. So you can run first some simulations, explore the space, then see, okay, these conformations here are quite interesting. Let's start new simulations from here. And if you're lucky enough, you might even find your bound folded pose. In general, you're probably going to explore much more of the conformational space than you would have otherwise. So you could say that there are two extremes. The one where your simulations have zero knowledge about what the other simulations have discovered before, and the other opposite where each single simulation knows what has happened in the past in the other simulations and learns from that. Our adaptive sampling somewhere in between because this is a bit inefficient if you just want to run. It's essentially like running one long, well, no, it's not the same as running one long simulation, but it would be really inefficient since we're doing stuff high throughput. So we do like batches of simulations. So we run a small batch of simulations. We create a Markov model in which we calculate some interesting new poses from which we're going to start the new simulations from. And we do this on and on and on in what we call epochs. These are, each one of these iterations, we call them an epoch. So there is this nice video by Vijay Pandey, which shows on the left adaptive sampling and on the right just a single trajectory. They all start from the same point, from the same initial place, and they all have the same aggregate simulation time. So here we're comparing really the same simulation time. And as you can see, the adaptive sampling here on the left is able to explore the space much, much faster than the single simulation, which is pretty much doomed there to stick forever in the first placing. While this one, if you wait a bit more, it actually also discovers a third state. And yeah, so as you can see, it can be really advantageous to run adaptive sampling. So we devised a protocol which works as follows. You start your adaptive sampling, you send the number of simulations, and max we call that. So let's say 20 simulations, you send out 20 simulations. You keep polling for completed simulations by retrieving them, so you see how many have completed. If enough have completed, you set like another limit, n min, which if you have less than n min simulations running at any time, you will create a new model. You will calculate new poses, and you're going to send out new simulations. And then you're going to do this in kind of a loop for as many epochs as you want. So here, this part of the MSM is kind of in dotted lines because you can practically also not do an MSM. You can do anything you want in this part of the algorithm. So that's a nice thing about HTMD, that you can plug and play different algorithms for adaptive sampling. So just to clarify this, n min and max is kind of like the maximum numbers of simulations that we want to have running at any time for this adaptive. So let's say 100. And then we define an n min, which is the lowest number that we want to have running at any time, which is like 20 or 30. The reason for this is that sometimes you don't really care for all of the simulations of an epoch to come back. You might also have, if you're working with a remote resource like GPU grid, it might take really long for all of them to complete because some have gone to some slow GPUs, some are some fast GPUs. So you don't want to wait for all of them to finish in every epoch. It's a waste of time, practically. So, however, once you reach the nmin, the number that you define, I mean, if you want them all to complete, then you just put nmin 0. If you wait for all of them to complete, once you've completed enough, so once you reach nmin running simulations, you just make a new epoch and you fill up the battery again with nmax simulations. Okay, so exploration versus exploitation. So there are different ways of doing adaptive sampling. One way of doing adaptive sampling, which we use by default until now, is to sample the least explored regions to identify new conformations. So if you imagine that we start from this double potential, we start a simulation here, it explores this space, kind of moving here. You see that it explored this space, and then we choose a new starting points, this green and the red one, because they are on the edges of the explored space, so they are the least sampled poses that we have seen in our simulation. So then we start these new simulations, the green one here, which maybe explores this area, then the orange one, which maybe explores this area. And then if we want to start new simulations, we'll start again from the least sampled areas, which are probably again the barriers, and then on and on. So as you can imagine, this method is very nice to overcome barriers, because it kind of in a stepwise manner, it keeps on climbing up the barriers to explore more space. So this is an exploration method. And then you can do something like exploitation, which was what we did in our first adaptive sampling, where you use some information that you're interested in to guide your sampling, but it's kind of like going downhill typically. So in this case, where we started Mesamidine binding to trypsin, we just started our new simulations from the most bound conformations of the ligand on the protein. And the most bound ones are the ones which are kind of deep in a basin. So essentially we were going down a gradient to the most bound conformation, which is here in the pocket. And this worked really nice for benzamidine trypsin because it doesn't have any real barriers to folding. So it goes pretty much in a uniform manner in like a nice pattern. It goes into the binding pocket. It doesn't go directly, like it has some intermediates, but the intermediates flow nicely into the bound state. So exactly, yeah, in benzamidine trypsin. So we started our ligand outside the protein. Here you have trypsin, the red pose, which you'll see also in the next slides, is a crystal pose. Here we build a Markov model out of our first epoch of simulations. And we see the main macro states here, the most metastable states. This is the free energy that the model calculated, and this is the most bound pose that it found, which is not the correct one. So here we started in the next epoch. You see that our green poses, which are again the starting poses, they are now not anymore in the bulk. They are in some places which are attached to the protein because these are stickier, let's say. They are bound stronger. And as you can see, okay, the model is still not correct. But if we keep going on and on, you see that more and more of those greens are getting close to the red, which is the crystal pose. I think it's crystal binding pose of benzamidine or trypsin. And as you can see, also free energy is starting to get lower and lower. And here, finally, the model recognizes that this place here is the bound pose, which is correct. It's actually the crystal pose, and also gives us a pretty good free energy, which then, okay, it goes a bit down, but it kind of fluctuates until it stabilizes to the correct free energy. Yeah, so this is a nice way of visualizing adaptive sampling so that you understand like where the simulations start from, etc. So the question is why use either exploration or exploitation? You could use both. So there are many also, we can also consider that there are many methods already developed that can predict some information, some structural information about our proteins. Like you can predict contacts, you can predict the secondary structure, allosteric sites. So you could use all of this information to guide your sampling to a region which you are interested in, if you have this information. So we have our exploration component, which we can call the unguided component. So this is also based a bit on work that we have done in the past and also work by Greg Bowman, who had a publication on this recently called FAST. So there's the unguided component exploration where, as I said, we're trying to overcome barriers, and then there's the exploitation component, which is trying to follow some gradient. And this gradient can be any gradient we define. It can be some general gradient like the solvation of the protein, the radius of gyration, its energy. Or it can be some more knowledge-based gradient, like the context, the secondary structure, the RMSD. If we know already the crystal structure, we might want to just get to the crystal structure. Exactly. So we have some experimental information, we have the prediction methods, and then we can combine them, use either, and combine both exploration and exploitation into the same adaptive sampling. One thing to keep in mind is that when you're following gradients, you need to be careful because you might get stuck, again, as I was mentioning, into one minimum and not get out of it. So what he was trying to show here, Bowman, in his paper, was that there are some gradients which actually flow pretty nicely downhill into the properties that you're interested in. For example, here he's trying to find the states of the maximum surface available solved available surface area, SASA. So as you can see, most of the pathways to reach like the highest SASA are pretty monotonically going there. There are some places where you need to go a bit back, but these are covered essentially by the exploration aspect. Since we combine exploration with exploitation, the exploration is able to overcome the barriers and flow nicely there. You can also think of it this way. So you start from here and you want to go here. The gradient that you would follow would be the straight line which goes directly there, but practically you would need to go over lots of mountains, which is very bad. It would take very long and also inefficient and not correct. So by adding the exploration aspect, you allow some flexibility to move around these mountains, but still go in the direction that you're interested in. And also not explore, for example, this area which you are not interested in this case. So here on the right, from his paper again, it shows nicely how conventional sampling, for example, doesn't find any conformations which have an interesting solvent accessible surface area. On the other hand, if he uses just exploration, which is this black one, he is able to find quite a few, but the most he finds obviously if he guides it towards the biggest SASA. The same is true also for RMSD, where conventional doesn't reach any lower than the starting one pretty much, while the exploration one goes pretty well, and then the one which tries to find the lowest RMSD obviously finds it. So if we look here at how many states we have discovered, which is kind of a way of looking at how much exploration we have done, we can see that, okay, the pure exploration obviously finds many more states, but still the guided ones also find more states than just naive normal sampling. So as you can see, it's quite interesting. If you have a goal where you want to reach, it's very practical to use such a method. So if we don't have any indication of what to look for, we would use only exploration, which was done until now with the adaptive MD class. If we know what we want to explore, and we do both exploration and exploitation, we can use adaptive goal class. Right now we are balancing by default 50-50, the exploration and the exploitation, but you can play around with it. There is still no clear indication what's the correct balance between the two, and probably depends very strongly on the system that you are looking at. So now we can move on to how we implement adaptive sampling in HTMD. We have the following classes: adaptive MD, adaptive goal, and then I'm also going to talk a bit about the naming convention that we use for adaptive sampling and about the queues, which we briefly presented now and you saw in some of the previous presentations. So, to understand how the file structure in HTMD works, as I said before, each simulation is a single folder. In our case, we don't put different simulations into the same folder. Pieces of the same simulation can go in the same folder, but not different simulations. The folders must contain all of the required files to run a simulation. In this case, it's imperative that if you have a starting folder for your adaptive sampling, it must be runnable. It must have everything that you need to run a simulation in it. Even in some cases, if you want, you can also run a save script which runs the simulation software, but we are going to talk about that a bit later. The name of the folder is also the name of the simulation, and as I said, it's a unit of execution in a way. So let's see, we have our two simulations here, our two starting simulations. Then we create a folder which is called generators in adaptive, and we put those in there. Well, let's say we had more. Let's say we had 4 initial structures. We just put them into generators. So these generators are contain all of the simulation files that we need to start the simulations, and they also contain like the initial conformations that we're going to start the simulations from. So what we do now in adaptive is that the adaptive, we link it to the generators. We tell it, here are our starting structures. So here are the generators. And now we start the adaptive. So what does it do? The adaptive creates a new folder called inputs. And it will take, so if we ask, for example, now nmax 9, so we want to send out 9 simulations into whatever computing that we have. So the adaptive needs to find 9 simulations, but there are only 4. So what will it do? It will just make copies of a few. So it will have 3 copies of 1, 2 copies of 2, 3 copies of 3, 2 copies of 4, etc. So now we run an epoch, the first epoch. So what does it do? Adaptive creates a new folder data where it's going to store the completed simulations in. That's, again, not necessary. If you want, you can configure the adaptive to store the simulations in the inputs folder if you want to have everything in the same folders. And then you link it to some resource like your local GPUs, for example, or Amazon, like AceCloud, or whatever you want to Slurm, your local cluster. Then adaptive takes those inputs and it sends them for simulation to your resources. Once the resources complete the simulations, they're going to store them in the data folder. And now you have exactly the same folders here and here, which match each other, which have the simulations here, and here the input files for the simulations. So how do we calculate now the next epoch inputs? Well, the adaptive sampling is going to take the simulations that we had from before, all of the knowledge that we have gathered. It's going to do some thinking. It's going to select some new interesting poses depending on what method we use. Like if we use the exploration aspect, it's going to find the least explored clusters in your data. And it's going to write starting confirmations for those interesting poses inside the inputs folder with new names like 5, 6, 7. I'm going to tell you later that these are not really the folder names. But and then we run the next epoch, which takes this 5, 6, and 7, the new simulations, and sends them to the GPU. And then the GPU returns the completed simulations. So you keep doing this in loops, essentially, in what we call epochs. So to sum up, if you want to do just the exploration aspect, the user needs only to provide the generators folder with these subfolders, which each one of them is a starting confirmation for your simulations, including all of the files that you need to run the simulation. The inputs and the data, and also the filtered folder, they are going to be created automatically by the adaptive, and practically you don't need to mess around much with them unless you want to analyze the simulations later manually. So let's look at the adaptive goal now. So if we want to do exploration and exploitation sampling, we need to define what we call goal functions. So these goal functions work as follows. So no, sorry, before I was saying that if you want to calculate a new epoch, you just took your data, you did some thinking, adaptive sampling, and wrote out some input, right? But now we need to define a goal function. The user needs to define a function which tells the adaptive which are your interesting poses, which are the poses which are closer to your goal. So the way that it works is that the adaptive is going to take your data folders, it's going to pass them to your function as molecules, so as molecule objects, which we saw in the first session yesterday. And then the user function must return, so okay, yeah, it passes as a molecule the first simulation. And then the user function must return a score for each frame of that simulation, a single score, so one number, which the higher that score is, the more favorable that poses for you, the more interesting it is. So if you're doing RMSD, for example, the lowest RMSD is the most, if you want to fold your protein based on RMSD to a crystal structure, the lowest RMSD is the most favorable one. So you should give a high score to the low RMSD frames. So it returns that to the adaptive, and then the adaptive passes it the next simulation. It calculates again a score, so it does it for all of the simulations. And then once it's calculated all of the scores, the adaptive is going to write out the new simulations. And that's it. And that will continue working as normal. So now to sum up the adaptive goal, you need to provide the generators, but you also need to provide a goal function. And that's pretty much it. Okay, let's talk quickly about the naming convention. So I lied a bit about these folder names 1, 1, 1, 2, 2, 3, because you cannot have folders with the same names, not even on your file system, and also we wouldn't want our simulations to have the same names. So also it would be nice if we were able to trace back where a simulation started from, like to see its history, to see its genealogic tree. So this here, for example, is from our adaptive runs, where we see that these are the epochs. Each line is one epoch. And we can see that this simulation here started from here, from this simulation, from that, from that, from that. So you can trace back a simulation like where it came from. And it's very useful also if you want to reconstruct like a super long trajectory from adaptive, you could do that because you could just join all of the pieces together and make one continuous trajectory. So the convention that we use for naming the simulations is the following. It looks a bit ugly at the beginning, but it's quite intuitive. So this is the name of the current simulation, which is E14, so epoch 14, S3 simulation 3. So yeah, because we have multiple simulations per epoch, which we send out. Underscore, this is the parent's name, where it came from, the simulation. And it tells you that it came from the simulation epoch 2 simulation 5, from the first piece of that simulation, because sometimes we split our simulations into pieces. It's not necessary. So typically you would see a 0 here, so don't care much about it. And this F25 says that it came from frame 25 of that simulation, of that trajectory. That's where that conformation, that interesting conformation was, from which we started our new simulation. So this way, yeah, we can construct the nice little genetic tree or a super long trajectory for visualization. So as I said, the naming is not really like this, 1, 1, 1, 2, 2, 2, 3, 3, 3, but in reality, it looks more like this. So in the first epoch, the parents are not as fancy as I showed you before in the previous slide. The parents are just the generator name. So if your generators are called 1, 2, 3, then it will have underscore 1, 2, 3 in this case. But the name is E1S1, E1S2, E1S3, until E1S9 in this case. So this is the naming that you're going to see in adaptive sampling. And next, I will talk about the queues, which are probably going to replace the apps, I think. Well, so the nice thing about the queues is that they're quite simulation independent. So we already saw the software simulation, sorry. We already saw the local GPU queue yesterday, which runs on your local GPUs. We also have a Slurm queue, which runs on Slurm. The AceCloud queue, even though that's not, I don't know how, it's probably not software independent. That one probably only runs ACEMD, right? AceCloud, I assume. And we are also in the next days, we'll probably also have an LSF and a PBS queue ready. So these ones are the ones that we can test, I think, so we can support those now. Yeah, we might even add others, but mostly by contribution of other users. So the nice thing about those queues is that they all have a unique interface. So they all have these 4 methods that you can call: the submit, which you give it a folder and it sends that folder for simulation; the retrieve, which in some cases it doesn't do anything. Like, for example, if you run locally, there's no retrieving to be done from a remote resource, but for remote stuff like AceCloud queue, it needs to retrieve the simulations from the remote resource. In progress, which tells you how many simulations are still running or queued. So from that you can infer how many have completed. And then the wait method, which stops the execution of your script until all of the simulations have completed from that queue. So yeah, they're quite nice queues because they're really simple and it's easy to implement new ones. So okay, we can now look at the code of the adaptive sampling. So let's go to folder 9 and open the 01 here. I think we won't be executing anything in this one. Just looking at the code. Well, okay, we'll execute the first one, which doesn't count. So here, just listing the folders which are available here, just to show you an example of what the generators folder looks like. Here I have a generators folder, which has some subdirectories. Actually, the 0 should not be there. I don't know why it's there. Okay, well, let's look at the next one, the NTL9. So you see all of these folders. Each one of these folders has all of the files needed to run a simulation. It has the input file for ACEMD. It has the PDB, the PSF, the parameters, so it's self-contained. This folder can run by itself. Yeah. So let's look now at the two classes, adaptive MD and adaptive goal. So we set up a local GPU queue, for example, if we want to run locally. Since adaptive sampling by default looks for your simulations in the data folder, you should also tell your queue to write your completed simulations inside the data folder. So that's what I'm telling you there. Once the simulations are completed, put them inside the data folder.
Which is not.
It's not necessary if you tell the adaptive that your data folder is the input folder. You can do that as well. Yeah. It's a matter of taste. Like some people prefer to have simulations with the input files. I split them usually. See 1 second. Okay. Then you set up your adaptive MD like this, and you set the app to the queue. We call it app because we used to call them apps, but we might change the name now. Then you set the n min and n max, so how many simulations you want to run in total, 10, how many you want to have running at any time up to 5, so once it gets under 5 simulations, it's going to send enough simulations to reach again 10, and the number of epochs, how many epochs we want to run. So now we need to choose what projection our Markov model is going to use, because internally the adaptive is going to build a Markov model to create the clusters to find the most undersampled regions of the space, as I was saying, for the exploration. So you need to define a metric to do that projection and clustering. So here I define, for example, we are doing protein ligand binding, which depends on the trypsin, I think. So I define the protein with name CA there at the top, and the contacts with the resonant band and 2 atoms of resonant band. Then I set an update period, which just means that your script is going, in this case, it's going to execute every 4 hours. And then I run that update. Be a bit careful with the update period, because if I put it to execute every 4 hours, but my simulations take 5 seconds, then obviously the adaptive is just going to wait and not do anything. So obviously put the update period to something that's reasonable based on your simulation time. And this is if you want to run the adaptive synchronously from your Jupyter Notebook. If you want to run it asynchronously, you can run it from crontab, for example, and then you just don't put any update period there. And it's going to execute the script complete and not do anything after that. So there are 2 options, running it synchronously with the update period or running it asynchronously. So the adaptive goal, most of the class arguments are actually identical to adaptive MD. As you can see here, you set up the app to the queue. You set the min and max, and then epochs. Here you see also how you can set a different generators path if you have them in some other folder. You can look at all of the arguments of adaptive goal. If you go to the documentation, also you can. It's quite well. Well, I haven't executed the initial sum, so well, doesn't matter. You can look at the documentation on the website or by pressing Shift Tab here. You set the projection, but the new thing that you need to do here is that you need to define this goal function, which is the one that will give the score to all of your simulations. So let's look at some examples of this goal function. So the goal function will take, as I said, as input a molecule object, and it will output a single vector, which for each frame of your simulation of that molecule object, it gives a score. It says, I like this one a lot, I don't like this conformation. I like that conformation, but not the other one. So the higher the score, the more desirable the simulation frame is for being respawned. So let's look at an example for our MSD. I load a reference molecule, the crystal structure, for example, and then I define this function here, which takes as input mol. So all of your goal functions must have as first argument mol. Then it calculates RMSD between the reference crystal structure and your molecule of the protein name ACA, it gives you an RMSD. However, the larger the RMSD is, the worse your poses. So you want to invert that actually. So you want to do minus RMSD, or if you want, you can even do 1 divided by RMSD or whatever. Whatever you can think of, depending on how much you want to bias or something. So if you have multiple arguments, so before I cheated a bit using the fact that in Python the functions have access to the scope outside of themselves, practically I would suggest not to do that and pass multiple arguments to your function. The first one, as I said, needs to always be the molecule because it will get passed automatically by the adaptive. The second one and the third one, and as many as you want, can be whatever you want. And as you can see here, I will be passing it the reference molecule. So then when you set the adaptive goal function, you need to pass it as a tuple, where the first element of the tuple is your function, and the second element is going to be a list of all of the extra arguments that you have after the molecule. Okay? Make sense? Okay, so you don't put mol here, just put ref and whatever else comes after ref if you have multiple arguments. So let's look at the secondary structure goal function. It's pretty much the same. So you pass the mol, a crystal, so the reference molecule again. You calculate the crystal secondary structure like this. You calculate the secondary structure of the molecule like this. Then you check how many of the secondary structures in the crystal are the same ones in your trajectories. So you do equality here. And then you sum over axis 1. You always need to think that the projections that we produce are a two-dimensional NumPy array in which each row is a frame. So if we want to sum like all of the, so this equality would give you 1 if it is the same secondary structure between the two structures. So if you sum it, you know how many residues have the same secondary structure as in the crystal. But you need to sum over axis 1 because that way you get a single number for each frame. If you sum over axis 0 accidentally or by not passing axis, you're going to be summing over. It will be weird. You're going to be summing over the residue instead of over the frames, so it won't even work probably. So then you return that score. Same for goal function for contacts. You calculate the contacts of your crystal, you calculate the contacts of your molecule, and then you sum over the axis 1. You check how many of those crystal contacts are actually also contacts in your simulation. You sum. If you want, you can also normalize it. It's not necessary. And then, oh, there's a mistake. This should be CO score. And that's it. So now we can try to do a short exercise. Where we'll try to theoretically unbind benzamidine for trypsin, but we're not going to run it because we're going to have another exercise afterwards, but you're going to write the code to do it at least. So we should go to the second file here, which is in the folder which is called 02, adaptive exercise. So it contains the solutions. Don't cheat too much by looking at them directly. They should be hidden by default, I hope, with this button here. So if you press that button, you see the solution, but try to do it without looking at the solution. If you really get stuck, either ask us so that we explain to you the solution, or, well, if you're too shy, I guess, look it up. But so the exercise is essentially, you have benzamidine, you start from the crystal pose. You start from the benzamidine stuck on trypsin, and you want to get it out of the pocket. So essentially, you want to break the 2 hydrogen bonds that it's making with the protein. Well, actually, I think it makes 3, but we are only going to try to break the 2 of them. So yeah, you're going to calculate the distance between the atoms of the hydrogen bond, and then just try to maximize that distance. That's the only thing that your goal function will have to do. But it's kind of a complete example because you go through the whole building, equilibration, and production runs. So yeah, you can get started. I will be around, so just ask me if you need any help, any questions. The documentation is on the website, but I have also added links here to the functions that you should use, so I think it should be easy enough.
Let's assume you have 2 proteins, open state and a closed state.
The same protein, closed and open.
Same. You give in your adaptive goal, you say, I want to reach the open state from this. Now, and supposedly you say that you've chosen 30 bonds.
Yeah.
Right? And you know from your free energy or what is the energy that is. How do you know at the end of the 30? So will the program at the end of 30 bonds get there, or
No.
so how do you define that? How many epochs get there?
The epochs you don't. It's not for me. It's not really an option. It's an epochs. I mean, we have it so that you can stop it at some point, but it's really a bad idea because you don't know how long it's going to take. I usually put it like 10,000 epochs or something, and then I just run until I reach that state. It doesn't guarantee you that up to something that within the epochs that you tell it, it's going to find your goal. You cannot do that. It's impossible. Then epochs is just an easy way of saying, okay, I'm done. Let's finish after this amount of sampling, let's say.
Okay.
So it's not really. It's like giving up. It's not like, oh, we completed after something.
Because it's unbiased, no? In any case.
Yeah, it's unbiased. So yeah. So I can't really force it to get there.
I was just thinking in terms of the parts that you get in for example. You have the same value, and you don't keep measuring until you get that point.
In this case, you can measure, but you don't push.
You don't push it.
Okay, so would you around
So yeah, you replace the comments that I have in the cells where it tells you do this. Just write your code there.
So another question: some people, not many, but 2 or 3, said that they found their own design and left them ones to analyze it together. Who are those people?